And we're going to get a little preview into some calculus. Like I said, we're going to make this, we're not going to get too far in depth, but we're going to learn some basic ideas as far as calculus. And today and tomorrow, we're going to focus on what's called the tangent problem. Okay, we're going to talk a lot about slope today. All right, we're going to talk a lot about slope today. All right. Students will be able to calculate instantaneous velocities and derivatives using limits. Okay, we've talked about limits this year when we found asymptotes. Okay, for example, we said something was a horizontal asymptote if the limit as, you know, let's say x approached infinity was some number. Remember doing that? We also talked a little bit about right-hand limits, right? As far as limits go, you know, limit as x approaches, let's say 3 of, you know, I'm going to change this. Give me a second here. I'm going to change this to infinity of f of x. If that was some number like 3, then we said 3 was a horizontal asymptote. So remember this notation? Okay, it's been a while since we've seen it, but we're going to talk a little bit about limits here. All right, we're going to talk a little bit about limits here. All right, and how they relate to what's, like I said, instantaneous velocities and derivatives. Those are kind of two in the same thing. All right, now it says if y equals f of x, then the average rate of change of y with respect to x on the interval AB is given by this little formula right here. Now this formula is nothing new, right? You learned this back in Algebra 1. I would say that's nothing more than the slope formula you learned back in when you first, probably some of you in 8th grade math, some of you in Algebra 1. Okay, whenever you took Algebra 1. Basically, that is nothing more than y2 minus y1 over x2 minus x1. All right, it's stating it in function notation, but realistically, that's just the slope formula. Okay, so if we're going to try to find the average rate of change of some function, all right, we just find the slope. Now, it says geometrically, this is the slope of the secant line through A, f of A, and B, f of B. A secant line is a line that intersects a function at 2 points. All right, at 2 points. All right, so for example, if I had this right here, I'm just going to make up a situation here. If I had the function f of x equals x squared, and we want to find the average rate of change on the interval, let's say from 0 to 2, right? Realistically, that's going to be the slope of this line right here, which is a secant line that intersects the curve at 2 places. Well, that's going to be nothing more than f of 2 minus f of 0 over 2 minus 0, which is going to be 4 minus 0 over 2 minus 0, which is 2. All right, so the slope of that line right there is 2. All right. Now, if we're going to try to find what's called the instantaneous rate of change, all right, we want to try to find what's called the instantaneous rate of change, let's say at 2, right? That's really going to be the rate of change at that specific point. Okay, so rather than having 2 points, we're going to have 1, right? So for example, if we wanted to find the slope of this curve at 2, we would form what's called a tangent line. Okay, and it looks like that yellow tangent line is a little bit steeper than the red line, so it would probably have a value bigger than 2. Agreed? All right. That's what we're going to look at doing today. And I know you can't read the word tangent very well. I'm sorry. Yellow doesn't show up very well on the green there. But we're going to look at how can we get to that tangent line, and it's going to involve limits. All right. But keep in mind, it's still going to involve this slope formula. Okay. That's slope. That's nothing new. All right. We're going to use it in a different way, but it's still the slope formula. So we're going to write a limit. It says we write limit as x approaches a, that's what that says there. I know it's written really small there. Equals L. We mean that if f of x gets arbitrarily close to L as x gets arbitrarily close to but not equal to a. Okay. So let's go back to that previous example I just had there. If we wanted to find, and I'm gonna use the same function, right? The rate of change or instantaneous rate of change of this function at x equals 2. And like I said, that would equate to what's called a tangent line. Right? So we have f of x equals x squared, and we're going at x equals 2. All right. What we can do is kind of start by doing what we did previously when we found the rate of change from 0 to 2. Okay. We know that the rate of change from x equals 0 to x equals 2, we just found that earlier. We said that that was 2, right? I'm going to put a little arrow here. All right. Now, that was between these 2 points. Now, what if we tried to get a little bit closer? What if I said a better estimate would be the average rate of change from x equals 1 to x equals 2? Would that be a better estimate? I'm going to draw this. Here was our first line, right? Here's our next one. Would that be a better estimate? Would that get a little steeper? And I wanted to go a different color. Sorry about that. That green one would be better, wouldn't it? Is it going to be closer to the slope of that red line? Yes. Right? This was 2. This is going to be bigger than 2. We want to get to that slope of that red line there, right? Which is a tangent line. The green and the blue are still secant lines. They're going to cross the curve at 2 points. Well, we can find that slope just by using our slope formula. F of 2 minus f of 1 all over 2 minus 1. What's that? That's going to be 3. Right? So is that a better estimate? I think it is. All right, I think it is. So if that works, should we get even closer? Should we try a point that's closer to 2 than 1? Here we went from 1 to 2. Let's get a little closer. Let's try x equals 1.5 to x equals 2. Find me the slope of f of x equals x squared from 1.5 to 2. Take a minute to do that. It's just a slope formula. And I think I know what it is because I've done this before, obviously. Shouldn't take a lot of time. I'm just telling you, I'm not trying to press you to get done, but this is not something that should take a lot of time. It's basically f of 2 minus f of 1.5 all over 2 minus 1.5. Once again, we're using slope. That's all we're doing. I'm trying to keep this simple. It's going to get a little more difficult a little bit later, not right now. 3.5? Keep working. You should get 3.5, I believe. Keep working. Once again, this is not anything that's over the top of our head. We're just finding slope. y2 minus y1 over x2 minus x1, which is really f of b minus f of a all over b minus a. Find slope. You've done this for years. You found slopes for years. Anybody got 3.5? Okay. Basically going to be 4 minus 2.25 all over 2 minus 1.5. Okay. Right. Well, if that's a better estimate than our first estimate. We went from 2 to 3 to 3.5. Let's get a little closer to 2. What would be closer to 2 than 1.5? 1.75. I'm going to go a little further. I'm going to say 1.9. That would definitely be right. Okay, I'm not saying you're wrong. I'm going to go to 1.9. Find me the slope from x equals 1.9 to x equals 2. That's a secant line also. All right, you should be able to find that. So yeah, this is Right now, finding slope, that's just some algebra 1 stuff right now. Realistically, all we're doing is finding slope. Once again, it's going to equate to a bigger concept, but right now we're just finding slopes. Right, so realistically, what we're doing as you're working, we're finding the slopes of 2 points that are gradually getting to be almost the same point, aren't we? Okay. And that's going to be something very important moving forward. All right. Should have got 3.9. Is that right? Should get 3.9. So does it appear that we're getting closer and closer to the actual slope? What do you think it is? 4. It is 4. Okay. And just for the purpose of getting a little bit closer, let's do this. If we go x equals 1.99 to x equals 2, well, what's 1.99 squared? Somebody just do that for me. What's 1.99 squared? 3.9601. So if we take 4, which is 2 squared, minus 3.691, is that right? 901. 901, okay. All over 2 minus 1.99, we end up with, is it 3.6901? All right, so I'm here, I was gonna say that can't work out. All right, so 3.9601. So that's going to be what? 0.309 or 399 over 0.001. Is that going to be 3.99? So are we getting closer to 4? We're all in agreement. We're getting closer and closer to 4. So we think the slope of this red line right here is 4. And the way we did that is we said, and we're not going to probably do it again exactly like this. But basically what we started with is we found the slope between 2 points, and then we gradually moved one of those points closer to the point we're looking for. Does that make sense? So we used the slope formula, and we basically said, as this number right here, as these numbers got closer to 2, we got a better approximation of the tangent line. We got a better approximation for the slope of that tangent line. Okay, and all we did is we kept using the slope formula. All right. Now, we're going to put this together here in a few minutes with a definition of a derivative, and we'll look at something else. But so basically, once again, a derivative or this tangent problem deals with slope, right? Deals with slope. You've dealt with slope for years. Okay, it takes things to a little bit different level, but we're dealing with slope. All right, now this one says use limits to find the slope of the tangent line to the graph of s equals t cubed at the point 1, 1. So here we're going to try to kind of put together what we just talked about into something and see if we can find this slope of this point, rather than finding a bunch of these slopes and get closer and closer and try to figure out what the limit is. All right, we can do it maybe more in one fell swoop. Okay, we can do this maybe in one more in a fell swoop. All right, let's try this and let's see if we can. We're putting things together here. Let's say it's the limit as t approaches 1 of, I'm going to say s of t, well, let me make sure I'm right here. hold on, don't start writing stuff down because I think I got to make sure I'm on the right page with this one here. All right. S of t minus S of 1 all over t minus 1. Okay, now let's just look at what we have there before we move on here. Now, would you agree that this, what's wrapped in blue here, is that nothing more than a slope formula? That's slope, right? That's a slope between some point and 1, right? Some point and 1, right? It's like f of b minus f of a all over b minus a. Now, this piece over here is using the other idea we kind of started developing there. If we do this and say the limit as t approaches 1, are we basically finding the slope between 2 points that are becoming the same point? Right? Just think about it earlier. As our value got closer to 2, didn't we get a more accurate picture of the slope? We went from 0 to 1 to 1.5 to 1.9 to 1.99. Okay. So as that value, 0 to 1 to 1.5 to 1.9, that got closer to 2, didn't it? Wasn't that number approaching 2? All right. So that's what's kind of highlighted here in green, or boxed up in green here. We're basically finding the slope of 2 points that are becoming the same point. That's what this is kind of getting us to. All right, and we'll probably look at a more formal definition here in a minute. Yeah, we'll get to a couple of those. All right, so that's really what we were doing on the previous problem, wasn't it? We were finding slopes of points that were of 2 points that were basically becoming the same point. Right, now how the heck do we figure out what this limit is? First of all, if I try to figure out this limit, what's going to be a problem right away? One way to evaluate a limit is just to plug in that number for t. Can I plug in 1 for t? What would I run into? Division by 0, okay? So I can't just plug this in and use the slope formula, right? So a lot of the important pieces of evaluating these limits is going to be algebra, okay? Remember, this is the function we're dealing with, it's t cubed. So this is really going to be the limit as t approaches 1 of t cubed minus 1 cubed all over t minus 1. All right, so this is a little more abstract. We're not working with numbers here. But if the function s is cube, whatever you have there, this is what we end up with. Okay. So the reason it's t cubed is because that's the rule. Just so happens that 1 cubed is also 1, right? All right. Now, what if I tried to plug in 1 for t right now? Did it get any better? No. It got worse, didn't it? Because what would I get? Wouldn't I get 0 over 0? Yeah. Holy cow. Now, this is where we're going to have to do a little algebra. There's a way we can evaluate this limit by plugging in 1 for t, but we have to do a little work. Okay, we have to do a little work. Now, earlier in the year, this is a long time ago, if we got 0 over 0, I think we said we could probably, that means the same value of t makes the top and the bottom 0 at the same time, and that's 1. So, could we factor this? Maybe you don't remember, but we definitely could factor that. Okay. All right, so this can become the limit, and I'm going to show you how to review how to factor it. We should be able to factor this out somehow. And what we end up with is t squared plus t plus 1. Now, how the heck do we get t squared plus t plus 1? Well, 2 ways. Back earlier in the year, or even maybe last year, you learned that there was a pattern for a difference of cubes. Is that a difference of cubes? Yes, just like a difference of squares is a pattern. You're not as familiar with this one, but there is one. Okay. The other thing is if we don't remember that difference of cubes, we could do this. What am I setting up there? Synthetic division. Okay, we could use synthetic division also. And what do I know? I know this is going to be what? I know that's going to be 0, don't I? Because that was 0. So if I synthetically divide by 1, here we go. 1. It worked out, didn't it? All right, we knew it was going to be 0, so we didn't do that to get 0. We did it so that we could figure things out. Is this where t squared plus t plus 1 comes from? Constant, t to the first, 1 t to the second. That's where that came from, okay? Didn't just grab it from the air. That's where it comes from. Either you remember the pattern or you're going to have to use synthetic division. Right? All right, so we're relying on a lot of that algebra that we've studied before. And that may not always be the case, but in this case, that's what we have to use. Okay? Questions? Now, what good did it do to factor out that top? Well, does it allow us to do this? Which means now we have the limit as t approaches 1 of t squared plus t plus 1. And now, can I plug in 1 for t? And I won't have that problem with dividing by 0 anymore, will I? We took care of it. So this is equal to what? 3. 1 squared plus 1 plus 1. All right, so in this problem, we really put together what we were doing previously, but we did it with maybe a more direct route. And factoring that's one of the ways we're going to be able to evaluate some of these limits, is we're going to have to do some algebra. Okay, we're going to have to do some algebra. The algebra here was factoring, and it helped us get rid of that division by 0 problem. That's going to be a big problem to deal with. All right, it's going to be a big problem to deal with.
What canceled out?
The t minus 1. T minus 1 canceled with t minus 1 here. All right. And this is the first time you've seen that process done. It's brand new, right? So it's not something you've seen before. I get that. Yes.
How did you get the 3 again?
Well, we said we couldn't, remember earlier, we couldn't plug in 1 for t because we got 0 over 0. But can I plug it in here?
Yeah.
1 squared plus 1 is 3. That's where I got it. Okay. The easiest way to evaluate a limit, if you can, is by substitution. Plug in that number. We plugged in 1 for t, and we could do that without having any problems. Up here we ran into problems. Okay. Yes.
So would this be like a more advanced version of like this type of problem? Because plugging in 1 didn't work, so we had to do something different to get like. Or is it always going to be like that?
You're probably, this is taking what we did previously with a lot of numbers to another level. We're going to have to deal with that division by 0 a lot. Okay, so you're going to have to be able to deal with that a lot. That's going to be common. All right, good questions all. All right, and here's maybe what they have a little bit. Same thing we have. I just tried to talk through it as we went through. They have the limit as t approaches 1 of t cubed minus 1 cubed all over t minus 1. It's really the same thing we just did. I just tried to explain things as I went. Okay. All right. Well, what we just found there, when we found a tangent slope, that's what we call a derivative. Okay. Realistically, all right, we just used or developed this idea. It says f prime of a. Now, this notation, this little, all right, this notation where you have that, little apostrophe there, that means that's a notation for derivative. Okay. Another notation for derivative you might see is dy dx. think of dy dx as delta y over delta x. That should revert back to slope, right? Change in y over change in x, isn't that what slope is? Okay. Now, realistically, we just found, in our case, we just found s prime of 1 by taking the limit as, it wasn't x, but it was t, big deal. T approaches 1 of s of t minus s of 1 over t minus 1. So can you see that we just used that idea? It's a different function name. It's not f, it's s. And we did it at x equals 1. Okay, so we just developed that. Okay, we just basically developed that. Now, what that's useful for is for what we just did. It's useful for finding what's called a derivative at a point. Right, it's useful for finding a derivative at a point. We found the slope of the tangent for s equals t cubed at t equals 1. We found the tangent line at 1. Tangent line and the derivative at 1 are the same thing. Okay. The word derivative is going to be instantaneous rate of change, slope of the tangent line. Okay, that's what the word derivative represents. All right. So the last sentence there says, geometrically, this is the slope of the tangent line. Derivative, tangent line, instantaneous rate of change, all really mean the same thing. Okay. And once again, it's nothing more than a limit associated with the slope formula. Okay. Questions on that? Now, this one is useful, but there's a derivative formula that might be a little bit more useful. This one will work when you're trying to find it as at a specific point. But this can be modified to this one. Okay. It says this one's easier for computing. I don't know that it's any easier. How does this one show up here? Well, let's look at this right here. If we had f of a plus h minus f of a, and then we'd have a plus h minus a, can you see what happens to the a's on the bottom? Can you see why that h disappeared? All right. So that's how it gets to that point. All right. Now, the one I think we're going to have that's more useful, and I'll tell you why, is going to be our next one. So we have, guys, basically 3 different forms of the same derivatives, but this one's going to be a little bit different. All right, first of all, let's use this one, or one of these two. Okay. This says find f prime of 3 if f of x equals 2x plus 4. Okay. All right, so rather than moving on, we're gonna step back and we're gonna use one of those 2 formulas we just talked about. Okay. You can use whichever one you want. It doesn't really matter. Okay, doesn't really matter. Okay. Let's look at this one. We're gonna find f prime of 3 by saying it's the limit as x approaches 3 of f of x minus f of 3, all over x minus 3. I'm going to use that one, okay? That's the first one we looked at, okay? Remember, f prime of 3 is going to find the rate of change or slope of the tangent line at 3. All right? So here we go. I'm going to move this over, actually. I'm going to move it over just, oops, trying to get the eraser here. I'm going to move it over here so I have a little more room here. Limit as x approaches 3 of 2x plus 4. That's f of x, right? I'll color coordinate this one. Minus f of 3. Well, f of 3 is going to be 2 times 3 plus 4. Are we good with that? It's going to be a number. It's going to be 11, right? Is that right? No, it's gonna be 10, sorry. All over x minus 3. Now, obviously, we can't plug in 3 for x because we'd be dividing by 0. But do you think there's some work we can do up here? What can we do up there? Simplify that? Okay. So we have 2x plus 4 minus, would it be minus 10? Is that right? Which means that's what? 2x minus 6? That's just the numerator. I'm just simplifying that. We good there? Which means this is like the limit as x approaches 3 of 2x minus 6 all over x minus 3. And I still can't plug in 3 for x because I'll get 0 over 0 here. So what should we do? Factor the top, right? Yeah. Limit as x approaches 3, we can take out a 2, and look at that. We ended up with a common factor of x minus 3 in both the numerator and denominator. And I can go there and there. And now we're left as a limit as x approaches 3 of 2, which is just going to be 2. All right, so there you can see that we're always going to have to deal with that division by 0 in some way, shape. Okay. This one was maybe a little bit easier algebra than the previous one, but we really just, algebra encompasses a lot of things here. Okay.
What's in the green parentheses in the numerator? Like 5 plus 2x plus 4.
F of 3, 2 times 3 plus 4. 2x plus 4 evaluated at 3 is 2 times 3 plus 4. Okay. Now, let's think for a minute here. Keep in mind the derivative represents the average or the instantaneous rate of change. What type of function did we start with? A line. What's the rate of change for that line all the time? The slope. These two agree. Does that make sense? Yeah. So for linear functions, finding the derivative would be easy. Technically, the derivative at any point of that line, 2x plus 4 would be 2. No matter where you did it. You did it at -3 or -6 or +10, it would be 2. Okay. And you can see there's the work. They use the other form. Doesn't matter. I use the. So there, I used the first form. They used the one that they said was easier, but I don't think what we did was difficult. All right, now what's going to be a little more valuable for us is to find what's called the derivative of a function with respect to x. Okay. This one is going to be the one we're going to use the most often. Now, what's different here? Here we're going to find a rule that will give you the derivative of a particular function anywhere. Okay, just said earlier that the derivative of 2x plus 4 is always 2. So at any value of x, the derivative is 2. All right? This is going to be a way we can find the derivative of a particular function at 2 or at 3 or at 6 or at -5 or at 13. Does it look very much the same? All right? What's different? Well, earlier we had f prime of a was the limit as, what was it, x approaches h, or h approaches 0, excuse me, of f of a plus h minus f of a all over h. Okay, that was what we just had. That was that one that was easier for computing. What's different with this new one? What's the one big difference? There's one main difference. It's x. A is replaced with x, right? So instead of finding, the one in yellow is finding a particular number. what we're looking for here, this will give us a number, right? If we evaluate that, we'll get a number. Okay. If we evaluate this one, we're going to get a rule. Okay. We're going to get a rule. Okay, so we're going to get a function.
Under limit, what does it say?
H approaches 0. H and that little a 0. Okay. These are also in the book. I know that these slides don't show up very large, but on page 740 and 741, if that helps. All right, this new one in this slide is basically, it's going to be more helpful. Okay, because if I know what function I'm dealing with, it'll find me I can find the rate of change anywhere. I can find it anywhere, okay? But we had to get there, okay? We had to get there. We've been kind of building up to this point. And we already talked about some of the algebra it takes when we're working with numbers. We're gonna have to do the same algebra when we're working with functions, okay? So here we go. We're gonna look at a couple examples here. Find f prime of x if f of x equals 2x squared. Okay, it's a 2 there, just so you know. So rather than finding f prime of 3, we're going to find f prime of x. The process will be the same. It's a little more abstract because we're going to have variables instead of having numbers. Okay, we're going to have more variables here. All right. Process is the same. It's going to be the limit as h approaches 0 of f of x plus h minus f of x over h. That's just the rule we just looked at. That's how we can find f prime of x. That's what was just on the previous slide. Okay. All right, now I'm going to do a little color coordinating with this next piece because sometimes this can get a little tricky. F of x plus h would be 2 times x plus h squared. Agreed? If we plugged in a number, we square it and then multiply by 2. F of x is right here, minus 2x squared. All right, and then we have h. Okay, so far so good. Now, in looking at this, we can't plug in, once again, our goal is to eventually plug in 0 for h and see what we get for our rule in this case, not our number. Okay, but we can't. Because if we put in 0 for h, I think I'd get 2x squared minus 2x squared up top, which is 0, and I'd get 0 on the bottom, right? So we can't do that. So we have to turn to algebra. Well, let's do some algebra here. There's nothing to work with on the bottom. I think we have to do some algebra up here. What should we do? It's the only thing we can do. No, we can't factor. There's nothing to factor, is there? It's already factored out, isn't it? How about expand? Okay, whatever, that's fine. So let's multiply that out. So we would have this piece right here would become 2 times x squared plus 2xh plus h squared. And then we have minus 2x squared, and we have all that over h. All right? So we're going to multiply that out. Okay? There's nothing else to do, right? Should have been obvious we had to do something with the numerator, all right? Now, if I continue to do some algebra, if I do a little distributive property here, I got 2x squared plus 4xh plus 2h squared minus 2x squared, all right? Instead of writing it all over again, I just did some work above there in blue. Well, what can happen now? Yeah, the 2x squareds are opposites. So they are going to, those are gone, right? So now I'm going to rewrite what I have left. Limit as h approaches 0 of 4xh plus h squared over h. Is it 2? It should be 2h squared, yes. It should be 2h squared, so I'll put a 2 in here. Okay, my bad. It's not going to matter, but it does matter to do this right. But you don't know why it doesn't matter yet, but I do. Okay. Now, can I plug in 0 for h? Still going to be dividing by 0. So what more can I do? Can I do some more algebra? I can factor out an h. I could factor out a 2h, but the 2 isn't going to be a big deal. Okay, I'm going to tell you that right now. But the bigger deal is that these all have a factor of h. So the limit as h approaches 0, I could say h times 4x plus 2h. All right, factored out an h. And then what? What have we done in the past there? Get rid of common factors, right? And once again, the whole goal here is that eventually we want to plug in what for h?
0.
And if we do that, does this become 0? And what do we end up with? 4x. So our derivative of 2x squared is 4x, which means if I want to find the derivative at 1, it's 4 times 1, it's 4. If I want to find it at -2, it's -8. For this function, I can find the value of the numerical value of the derivative by plugging in x. Does that make sense? So this is a rule that works for that function anywhere. Anywhere. Okay. And yes, there's a lot of algebra to do here. Here we expanded, we took x plus h and squared it. I did it maybe quicker than you can, but you don't have to do it in a big hurry. We expanded x plus h squared. We used the distributive property. We eliminated like terms. We did some factoring. All things that we should be capable of. All right, all things we should be capable of. All right. There you're going to see very much the same work. So do you understand now why the fact that it was 2h wasn't important, but we wanted to make sure, right? Okay. All right. Questions? All right. Now, we're not going to go away from derivatives this week. We're going to continue talking about derivatives tomorrow. All right. Actually, at the beginning of class, I've probably got a couple more examples to look at, or maybe we'll look at those examples from the text. All right, but here are some questions to look at for tomorrow. You're gonna, hold on. You're gonna have to learn how to find a derivative, guys. I'm telling you right now. Let's go ahead. Right, you're gonna have to. All right. Will this be on the quiz we take over chapter 10? Yes. Yes. Could it be on the final semester final? Yes. All right. Here's some questions to look at for tomorrow. This isn't something you're going to pick up just and figure out how to do without practice. We're not moving on to section 2 until next week.